Good evening to all and good evening, sir. So the main intention is, sir, to recall, remember and rise. Recall means on this occasion, the JK's birthday, 142nd birth anniversary. So it is our primary responsibility to recall their life and their contributions, and we need to remember their contributions and their life, and at the same time we need to rise. So means, for example, in any journey of geotechnical engineer. So if any demotivation will come, then to me, Kesagrande life journey is always a motivation to me. So we know like Atterberg limits we know, but what is his life? So we don't know. So we know Darcy's law, but permeability equations, but we don't know about his life. So my intention is not only his contributions, means we read most of the times in textbooks about liquid limit, plastic limit, but how much time it has taken to come up with that limits, right? And we talk about the shear strength of the soil is a very important parameter, but how that equation comes, and what is the Coulomb has done. So we call it as more Coulomb, but what is the contribution of more and what is the contribution of Coulomb, and what is their life struggles, how they started and what they want to become and what they become at the end. So this is the background thought to me while reading this author's life. So why can't we make one lecture or one video so to discuss about their lives. So their contributions we read many times in our textbooks, and we heard most of the lectures, seminars about the topics, and the authors names multiple times, but how their life started and what is their family background and what is their education and how they started. So that is the background thought process to make this particular life and contributions of our legends in soil mechanics. And I have considered only very popular and few people, and who are the father of soil mechanics and father of modern soil mechanics and great legends who contributed major things in geotechnical engineering. So coming to first one is Charles Augustin de Coulomb, and de Coulomb is the first father of soil mechanics. So Terjege is father of modern soil mechanics. So he was a French engineer. He was born in France in the city of Angoumois. Angoumois is the city, and the place is Angoulême, and he was born in this place and in the date of 14th June 1736. So he is a French officer, engineer and physicist. And coming to his father, Henry Coulomb, an inspector of royal demesnes, originally from Montpellier. And so we can say that his family background is very good. So he is from military background, a lawyer demesnes. And mother, Catherine Bajet. So coming to his studies, he studied at College of Mazarin. Today the college is called Institute of France, and till now the institute is working. And coming to his studies, he included philosophy, languages, literature, you know literature. He also received good education in mathematics also, astronomy, chemist and botany. So he studied all these topics. When his father suffered from a financial setback, he was forced to leave Paris and went to Montpellier. So that is the thing. And Coulomb submitted his first publication to the Society of Science in Montpellier during this time, and he went back to Paris. So passed the exam for military engineering studies. So in 1760. So his major studies done in the military background. So he studied Royal School of Engineering in Mezieres and military engineering studies at the age of 24. So he completed. So coming to his degree, so he graduated. In the year 1761 and joined the French army as an engineer with the rank of lieutenant. So he is majorly worked in the industry type. So we can call it as a army. So over the next 20 years, he was posted to a variety of locations where he was involved in engineering, structural, fortification and soil mechanics, as well as other field of engineering. So then he began to write important works and applied mechanics and presentation his first works at Academy of Sciences in Paris in 1773. In 1779, while serving as a military engineer, he published his important work, Theory of Simple Machines, with regard to the friction of their parts and rigidity of ropes. So this is the major work, and this was a landmark study on friction loss by the Coulomb, and he is best remembered for the Coulomb's law in electricity. So even the unit for the electricity charge we use today is Coulomb's law. So units are coulombs. That units came on his name only. Coming to geotechnical engineering point of view, so Coulomb addressed the Academy of Science in the year 1773, presenting a modest essay on the application of rules of maxima and minima to statistical problems. So that problem of statistic problem solving, maxima and minima, that comes the theory of earth pressure. So this essay printed 3 years later by the Academy and is the earliest publication of soil mechanics theory. And this is the first publication and scientific publication in geotechnical engineering. This is the first scientific publication, and it started the active and passive earth pressure concept. The friction concept was known and newly invented at that time, and Coulomb added the cohesion term to it. So whatever the shear strength equation today we are seeing, tau is equal to C plus sigma tan phi. So in this tau is equal to C plus sigma tan phi. Tau is equal to sigma tan phi is earlier already existed. So what Coulomb did, Coulomb added the cohesion term to the equation, and the equation today we are using by the Coulomb equation, C plus sigma tan phi, and he used it almost the same way. So he added the cohesion term in coming to geotechnical engineering. So these are the contributions of Charles D. Auguste Coulomb. This is the shear strength of the soil, and this is the UCS. So if you do a UCS sample, then cohesion is equal to half of the uniaxial compressive strength, and these are the earth pressure calculations, and height of the vertical cut without any support, and this is the passive earth pressure. These are the contributions of the Coulombs at the initial stage, and this is the early study on geotechnical engineering. Coming to this is all about Charles D. Augustine Coulomb. He is the grandfather of soil mechanics. We call him grandfather of soil mechanics. Coming to Henry Philibert Gaspard Darcy. So we know Darcy's law majorly while studying permeability of the soils. He is also from France, French engineer, and he was born in Dijon. And despite his father's death in 1817 when he was 14, so when he was in 14 years old, his father was dead, and his mother was able to borrow money to pay his tuition fees. So it's such an inspiring story that the 14-year young boy lost his father, and his education was done on borrowing money, and he studied in 1821. He enrolled in Polytechnic College in Paris. So Polytechnic College in Paris, and transferred 2 years later to the School of Bridges and Roads, and which led to employment in the Corps of Bridges and Roads. So he joined as a job in Corps of Bridges and Roads in Paris. So he built an adequate pressurized water distribution system. He is the man and who has the major role to supply the pure water, drinking water, to the city of Dijon, and the system was fully closed and driven by the gravity. A network of 28,000 meters pressurized pipes was done, and all these were done by the gravity only, no any external pump pressure. Then in 1848 he became chief engineer at Dijon, and due to the political pressure, and he left the place over here, and he joined again Paris, and chief director for water and pavement, and took up office in Paris. So he joined in Paris as a water and pavements division in Paris. So now his journey started in Paris. So he was able to focus more on hydraulic research, and especially on flow and frictional losses in pipes. In hydraulic mechanics we hear that Darcy-Weisbach equation. So that Darcy is the person, he is the only given by on his name, a Darcy-Weisbach equation, and Darcy is the contribution. During this period, he improved the design of pitot tube. So to know the fluid pressure and how much pressure it is having the fluid while fluid is flowing, that pitot tube, and he was the major contribution. He made the changes, and still today we are using that one. and that studies around 1845 to 1855. Approximately, he has given 10 years of research on hydraulic to come up with the pitot tube changes and Darcy waste base equation and frictional losses on pipes while a fluid is flowing. So these are his research area. So in 1855, due to his poor health, so he resigned from his post in Paris. So he resigned his post in Paris, and again he back to Dijon in France. So and he where he was permitted to continue his research. So now after retirement, he performed numerous experiments of flow resistance in pipes in open channels, Darcy, and seepage flow in porous media, and he gave two name to Darcy waste base equation what I mentioned. Then Darcy's law of groundwater flow motion, which states that the seepage flow rate is proportional to the ratio of head loss over the length of the flow. So whatever the hydraulic gradient difference, permeability and seepage. So that was given by the Darcy, and it was discovered by the Darcy, and who showed that for a flow of liquid through a porous medium, the flow rate is directly proportional to the pressure coefficient. And this he come up with the equation, Darcy's law, after his retirement. So he was lived up to approximately 57 years. So in this 57 years, he started his research, and he come up with the Darcy's law at the age of 55. So after retirement, it's a motivation that there is no age limit to do a research, to continue a research, and still we can achieve our dreams, and still we can achieve what we thought while entering into our field. So that is the main motivation thought behind when we read Darcy's biography, and he was died on 3rd January 1858. Next, coming to Rankine, and Rankine was born on 5th July 1820, and Scottish mathematician and physicist. Here it is the Scotland, and he was born in Edinburgh. Rankine was born in Edinburgh, and father was David Rankine. His father is also a civil engineer from military background, who later worked on the Edinburgh and Deccan railways. Mother Barbara Graham, a prominent legal and banking family, means his family background is very well established. William was initially educated at home due to his poor health. Next, but he later attended Higher Academy and then High School of Glasgow. Here it is the Glasgow. Next, in 1834, he was sent to the Scottish Naval and Military Academy. So his father is civil engineering, and he has a military background, and his education is also from Naval and Military Academy. In 1836, Rankine began to study a spectrum of scientific topics at the University of Edinburgh, including natural history. So he studied at Edinburgh. Next, he left the University of Edinburgh in 1838 without a degree. So here is the twist. So Rankine, discontinued his college degree, and he joined as an apprentice. So an apprentice to Sir Benjamin McNeill, and who was at the time a surveyor to the Irish Railway Commission. So this is more interesting point. So he left the degree and he joined as an apprentice. Then he come up with the works, Rankine method for laying out railway curves, fully exploiting the theodolite and making a substantial improvement in accuracy and productivity over existing methods. In 1850, he was elected a Fellow of the Royal Society, Edinburgh, and he won the Society of Keith Prize for the period 1851 and 1853. And from 1855, he was Professor of Civil Engineering and Mechanics at Glasgow University. So, can we imagine that the person who don't have a degree, he become at the end as a professor, at the university, and professor of civil engineering. So this is a motivation, like means even if you are not achieving or if you are not done anything on our past timeline, still there is a scope to continue our hope while reading this great legend's biography. Still there is a hope to do and to continue our dreams. Next, Society's Vice President from 1871 and 1872. The Rankine lectures organized by the British Geotechnical Association, so who don't have a degree. So on his name, so every year, a Rankine lecture is organized by the British Geotechnical Association. So this was started in the year 1961. Till today, a Rankine lecture is organized by the British Geotechnical Association every year in the March. That is the contribution, and that is the level of dedication in geotechnical engineering by the Rankine. So contributions, fatigue in metals of railway axles, applied mechanics, steam engine and other prime movers, thermodynamic cycles of events. In soil mechanics, notably in lateral earth pressure theory, stabilization of retaining walls. These are the most recognized works in geotechnical engineering or soil mechanics. And coming to awards and honors, he received many awards and honors. So that is very impressive. The person who left the degree and who later achieved highest awards in the academy. And his books, a manual of applied mechanics, manual of steam engine and other prime movers, a manual of civil engineering, shipbuilding, theoretical and practical, a manual of machinery and mill work. So these are the classic books by the Rankine. And he was died on 24 December in 1872 at the age of 52 years. So next coming to Atterberg. So Atterberg, Atterberg limits. When we enter into our graduation studies, so we know his name, but his background is quite different. So he was from Sweden, Swedish chemist. See, he is a chemistry background and agricultural scientist. So Atterberg received his PhD in chemistry from Uppsala University in the year 1872 and then stayed there as a lecturer in analytical chemistry in 1877. So he was born in 19 March in 1846, and I was tried to gather his family background, but I was unable to find out. And this is the information available about him on the internet. He traveled across Sweden and abroad to study the latest development in organic chemistry. Then he went on to become a principal of chemical station and seed control institute at Kalmar. This is also in Sweden. So it was towards the age of 54. Okay, so that Atterberg, while continuing his work on chemistry, began to focus on his effort on classification and plasticity of soils. So at the age of 54 years, so his primary research, basically on chemistry. So at the age of 54, it turned to classification and plasticity of soils. So from 1900 to until his death 1916. So he devoted mainly to the study of soils and their physical properties. So whatever the properties today we are calling Atterberg limits, so it took around 16 years to come up with the proper establishment. So can we imagine few people in industry and few people in academics. So people says that I'll touch the soil and I'll tell the liquid limit. So I'll touch the sample and I'll tell the plastic limit. So people give like that statements, but the background story and background time, it has taken 16 years. Can we imagine that? So we just think of that in the laboratory also we took very lightly for the determination of liquid limit and plastic limit, because of these are just for the classification and not impacting any design. That is the reason. So but the background pain is very hard. Coming to the clay, the proper definition of the clay. So when the particle size is less than 2 micron, then only we call it as a clay. So this 2 micron window, this classification given by the Atterberg. So before that we do not have, right? So next, apart from that, he started doing the work on sedimentation also. Means he decided, however, that sedimentation for the characterization purpose, but it was too slow and impractical. So here I want to just say that he directly not come up with the Atterberg limits. He made different trials and different methods also. So he tried on sedimentation methods also to find out the physical properties, but he come to know that this is too slow and impractical of sedimentation process. Then he shifted to plasticity of the soil particles. So in the 16 years, it is not about the Atterberg limits, it's about failures also. So the process what he believed and what he made trials on sedimentation, that was not come as a truthful result. So that was not yet reported, and that was not yet used in geotechnical engineering. Okay, so next set out determine the physical properties peculiar to different soil types. Next, Atterberg work on soil classification gained formal recognition from the International Society of Soil Science in Berlin conference in the year 1913. 2 years later, US Bureau of Standards report stated that Atterberg method was as simple a one as could be devised, and it was well that we should become familiar with it. The US Bureau of Chemistry and Soils adopted it in 1937. So after this, reading this statement that Tejagi was Atterberg was died in the year 1960, and it was adopted by the 1937. 16 years of after his death, it was adopted. So he has not seen his success of his what we called research. And coming to Atterberg limits by Casagrande apparatus, that apparatus also came after 1930. So that is a very inspiring story of Atterberg. So the importance of Atterberg work has never been fully realized in his own field of agricultural science, nor in other subject concerned with clays, ceramics. So basically, he devoted to his entire life to agricultural science and ceramics as a chemist, but his its introduction to the field of geotechnical engineering was due to Carl Tejagi. Because of the Carl Tejagi, who came to realize its importance at a relatively early age of his research. Tejagi assistant Arthur Casagrande standardized the test in his paper in 1932. So he was died in 1960. Testing apparatus came in the year 1932, and procedures have been followed worldwide over the science. And he was died in 14th April 1960. And one more point also I would like to mention here is Atterberg limits means we know liquid limit, plastic limit, and liquid limit, plastic limit, and shrinkage limit. But Atterberg has given 6 limits. So even we have sticky limit also. Sticky limit means the water content at which the soil particles move away from the metal, so it won't stick to the metal plate. So that limit also given by the Atterberg. And cohesion limit is also there. The water content at which the cohesion between the two particles is separated. So that cohesion limit is also given. So like that 5 points. But in geotechnical engineering we basically use 3 limits. And this is about Atterberg. So from the life of Atterberg, we should remember that it's always a scope, to learn and to do our duty, and things will happen automatically after the time, and when it comes to its own time. That is what I believe when I read Atterberg. Next, coming to Carl von Tejagi, and he was born on October 2nd, and in the year 1883. And his father was Army Lieutenant Colonel Anton von Tejagi of Italian origin, and Amelia in Prague. He was born in Prague. This is the area of the Prague. Initially it was called as Austria. After division, now it is called as a Czech Republic. Here is the Austria, and he was born in Prague, and now it is called as a Czech Republic. In 1900, Tejagi entered the Technical University in Graz in Austria to study the mechanical engineer, and where he also developed an interest in theoretical mechanics. Theoretical mechanics also there. And this is the Austria, and this is the place of the Graz. Now, while fulfilling his military obligations, Tejagi translated a popular English geology field manual into German and greatly expanded it. So most of the people say that a mechanical engineer how started his interest in geotechnical engineering. What I believe that this is the turning point of Tejagi. So where he translated popular English geology, and this is the geology book, English geology book, and translated into German. So while translating, he read very deeply about each term and meaning of the each term. There he got more interest in geotechnical engineering, what I believe. So next, he returned to the university for 1 year. So means after 1 year of military work, and he came back to University of Graz. and combine the study of geology with courses on subjects such as highway and railways engineering. This is another turning point to get interest in geotechnical engineering. Shortly afterward, he published his first academic paper on geology of terraces in southern Styria, and this is the first publication. This is geological and geomorphological features of terraces, how they form. And coming to, he developed some novel graphical methods for the design of industrial tanks, and which he submitted as a thesis for his PhD. So he directly not entered into the academics. He first joined as a trainee engineer in an industry. In the industry, while working, he developed some graphical methods. Those graphical methods submitted as a PhD degree at the university. Now he became a professor at Royal Ottoman College of Engineering in Istanbul. Now it is Istanbul Technical University. Robert next after that, due to the political pressure, he shifted to Robert College in Istanbul. Now he began studying experimental and quantitative aspect of permeability of the soils. In 1924, he published the Mechanics of Earth Construction based on soil mechanics. This is the first book written by the Terjagi. This book was written in the year 1924 in German language. So the English version published in the year 1925. Even if you search in Wikipedia also, the first book written by the Karl Terjagi, by most of the citations says that 1925, and most of the very few places says that 1924, right? So if you take like that, and 2025, this year is 100 years of English version of Terjagi's book, that is the Mechanics of Earth Construction based on soil mechanics. Then that resulted in a job offer from the MIT Institute because of that textbook publication. And here it is the MIT in the USA. So he gave a plenary lecture at the International Conference on Soil Mechanics at Harvard University and International Society for Soil Mechanics and Geotechnical Engineering. Terjagi was first president. This was organized by the Casa Grande. We come to know in the next Casa Grande thing. Next, the American Society of Civil Engineers established in the year 1960 Terjagi Award. Next, Terjagi and Peck Library, so which is managed by the Norway Geotechnical Institute, Oslo, Norway, holds an extensive collection of his papers. So his library still is there in Norway. So next, the Mission Dam in British Columbia, Canada was renamed in his honor as Terjagi Dam in the year 1965. So Terjagi's famous quote is, I recognize weak points in traditional procedures and try to make them less weak. Sometimes I fail, but usually I succeed. So this is his statement, who worked and who dedicated his life. So his statement is, he tried to make less weak. So that is very impressive statement. So most of the times we state that I want to eliminate that, I want to modify that, I want to make new system, that we comment on that on our small research of masters of degree and PhD degree. We make statements like I'll change that, I'll remove that, like that. But who dedicated his life? He is saying that he want to make them less weak. So very appreciative statement. It's a very motivating whenever reading about this statement. So coming to geotechnical engineering, the theory of effective stress was developed by Terjagi in the early year 1920s. Okay, water saturated, and this is the effective stress concept, and this is the effective stress control stress strain rate. Terjagi theory was successfully used for solving problems in consolidation of porous permeable soils, for explaining reasons of sand liquefaction during earthquake, as well as several other tasks. So most of the times I get doubt that means why Terjagi called as a father of modern soil mechanics and why not other people. For example, work point of view, contribution point of view, most of the times I feel like Casa Grande did most of the work, but why Terjagi? Because of this effective stress concept. So the effective stress concept changed the entire perspective of geotechnical engineering, and the calculation of stresses, loads, strains, deformations, settlement, all these things means most of the stress related applications changed by one theory. That theory is called theory of effective stress theory, and theory of effective stress. And because of this theory, he is the father of modern soil mechanics. Now coming to Arthur Casagrande, and Arthur Casagrande was born in Advosia in present-day Slovenia at the time of Austria-Hungary, and his American civil engineering was in August 28, 1902. Then he moved to this is the place, Slovenia, and he moved to Trieste after attending his first year in school in Linz, and here it is Trieste, and here it is the Linz. So when reaching the age to enter the secondary school, he entered into a real school where students are typically expected to take an apprenticeship and pursue a technical career upon graduating. He graduated from Technical Institute Vienna, so with a civil engineering degree in 1924. After which he carried on moving there a full-time assistant to Professor Schaffernak in hydraulic laboratory. So after his degree, he worked as an assistant for a professor in the hydraulic laboratory. Next, when Casagrande's father was died in 1924, and the duty of supporting the financial burden of the entire family, together with a strong desire to engage in major civil engineering projects, promoted to take the gamble of moving in the United States. A decision that was not supported by his mother and professor. So after his father's death, he decided to go to United States, but this was not supported by the mother and professor. But he took a strong decision. So Casagrande stayed in hostel 10 days after arriving in New York in the year 1926 and decided to go New Jersey and work as a draftsman. So sometimes I feel like what Casagrande wish. So his wish was to become a draftsman, right? In New Jersey. So how life changes, and how he's become such a great legend in geotechnical engineering. From New Jersey draftsman to Harvard University. It's not a joke, and it's always New York to New Jersey. So to become a draftsman. So while visiting MIT Institute for a job interview, so he met Carl Tejagi. This is the turning point of Casagrande, who had only just arrived, and so we seen that Carl Tejagi first book was published in the year 1925, English version. So that book led him a job in MIT. Tejagi, right? So he was in the year 1926. He is very new at MIT Institute, Tejagi, and at the same time in the year same 1926, he met Tejagi, and Tejagi, who had only just arrived and was immediately offered the job opportunity to work as his private assistant. So Tejagi given a job to Casagrande to work as private assistant. So from 1926 to 1932, Casagrande worked as research assistant with the US Bureau of Public Roads, assisted to MIT, where he assisted Tejagi. So he worked on the supervision of Tejagi. When Tejagi took up a professorship at Vienna, so in the year 1929, again from MIT to he joined Vienna in the year 1929 after a short stint at MIT. Then, so Casagrande traveled with him. So when professor from MIT to Vienna, so Casagrande also traveled with him to establish a soil mechanics laboratory. That would later become one of the most famous research centers in soil mechanics. So that first laboratory was established in Vienna, Austria, and that laboratory was established by the Casagrande, and that is the most famous research laboratory. At MIT, he developed the liquid limit apparatus. So here comes the liquid limit apparatus. This liquid limit apparatus for the Utterberg limits, and the hydrometer test, the horizontal capillary test, the odometer operator, the box shear test, all of which still from prototypes from one used till today. So most of the laboratory equipments, designed by the Casagrande, and till today we are using Casagrande apparatus to estimate the index and engineering properties of the soils. He was also pioneer of the conducting triaxial shear test, and was one of the first persons to study the volume changes of soil during shear. The common procedures in use today for the identification of pre-consolidation pressure. This is pre-consolidation pressure, that graphical method given by the Casagrande for over-consolidation soils due to Casagrande. Okay. In relation to his work, Atterberg limits A line. So in the plasticity charts, we find that A line is there, right? So that A line means A stands for Arthur. So this A stands for Arthur, and A means Arthur Casagrande. It's a dedication to Arthur Casagrande. So plasticity chart will be named after him only. In 1932, Casagrande moved to Harvard University, where he would later be promoted to a newly created chair of soil mechanics and foundation engineering in 1946. So from what I said, that draftman to Harvard University. So again here helped by the Terjaki. There he rapidly established a school of postgraduate teaching and research that would see the number of students steadily grow from 12 in 1932 to 80 over World War time. So 12 students to 80 students started. At one stage during 1942 and 1944, Casagrande went on to train a total of approximately 400 army officers. So he trained army officers also at the time of World War II. And even Terjagi would later join the Harvard University. After that, Terjagi joined Harvard University. Then the successful soil mechanics foundation engineering program at Harvard. So the first, till today, whatever the soil mechanics program is running at Harvard University, first was given by the Casagrande. Casagrande was also credited for organizing the first ever international conference. So in the Terjagi's life, we come to know that International Society for Soil Mechanics, that conference president was Terjagi, but that was organized by the Casagrande, International Conference on Soil Mechanics and Foundation Engineering in 1936, which Terjagi considered to be too much of the gamble given to early stage in soil mechanics at that time. Okay, so this conference establishment of the International Society for Soil Mechanics and Geotechnical Engineering. So Casagrande's passionate interest in earth dams and extensive research work he was carried out on seepage as well as soil liquefaction. Even though the word liquefaction, so the word liquefaction is there, no? So the word liquefaction was first coined by the Casagrande, and proper definition was given by the Casagrande in the literature. Casagrande won many awards throughout his career, including being named his first ever Rankine lecture. The first ever Rankine lecture, so we discussed about the Rankine lecture started in the year 1961. That first lecture given by the Casagrande, what a biggest honor to give the Rankine lecture. That is the first lecture, and BGA as well as Terjagi lecture, and he given Terjagi lecture also. So this is the plasticity chart, and this is the A line. This A stands for Arthur, and this is the Casagrande apparatus. So in 1932, and after 5 years of multiple tests, so we take very lightly about liquid limit by Casagrande apparatus, but to come up with that design, it took 5 years. So by making many trials and errors, Casagrande finished the design of the instrument that today is known as the name of the Casagrande curve, which is still used today to determine the liquid limit of the clays. So this instrument take 5 years to come up with that. And after all these biographies, so I was more passionate about Casagrande. So we have two options. So just be a Casagrande or make a Casagrande. If you are a good position, then train any student. Give more opportunities to work more and more liberal. And that's it. Thank you for attention.